All right. Good morning, everyone. Everyone have a good Labor Day? Did y'all get to do something fun? Anything fun? Okay, well, that's a disappointment. It's always good to have fun. So we're going to have fun in here today. Does that sound good? Hopefully we're going to have fun in here today. Brought some props, so we'll get to those in a little bit. Any questions before we jump into the material today? I was told that the schedule wasn't letting you download it for some reason, so I'll take a look into that some more today. It looks, from what I can see, that it's published. Canvas is kind of weird when it comes to making sure stuff's published, but we're going to be talking about networking topologies, connectors, and wiring standards. So I'm just going to go ahead and switch over to the screen here. All right, so specifically what we'll be covering today is different physical media, which is really just a fancy way of saying cables. We'll be talking about different properties of the cables. We'll be covering the wiring standards. And lastly, we'll be talking about installing wiring distributions. So, right off the bat, like I just said, with physical media, all we're talking about is passing a signal across a cable or some physical medium. In the context of networking, we're almost always talking about a cable. That's going to contrast with broadcast mediums where we'll be using wireless, for example, Wi-Fi. So those are certainly things we want to keep in mind, is that we're always talking about physical media. It's just a cable. So one specific type of cable is the coaxial cable, and I've brought some samples of them. If you would please, I'm going to pass it around, but please don't unravel it. It's a real pain to get it wrapped up nicely. So basically, it's just a cable that has a copper conductor, and I don't know what I just did. Anyway, it has a copper conductor in the center, and then it has a dielectric insulator around that copper conductor. Then it's going to have a shield, and it's going to have, finally, an insulator. So the insulator can really be two types. The first is probably going to be more common for home installations whenever you have just something going from the wall. So for example, if you were plugging it into a jack, you'd almost always use PVC. Now in contrast, if you were to use something going through walls or especially breaking any sort of fire barrier, you're almost always going to use some sort of an FEP material. So more common way to refer to that is Teflon. And there's a couple reasons for that. First of all, what happens to PVC when it burns? Does it burn? It melts and it also burns. So I thought about asking if I could do a demonstration outside today where I lit a cable on fire. I just didn't think that'd be a good idea. So anyway, we're not going to do anything crazy like that. But I tried to find a video online. Seems like no one else was crazy enough to do it either. So I'm not suggesting that anyone in here do that. Let me be clear. But if you do, make sure to take a video of it. But again, I'm not suggesting it. So Teflon is going to really sort of mitigate a lot of those problems. And it's going to allow us to run cables through a fire barrier as long as we make sure to insulate well with fire-rated compound around the cable through the penetration in the wall or ceiling or wherever. It's not going to allow fire to pass through it. Now beyond that, another important note, what happens to PVC when it burns? It also has toxic smoke. It's not good to breathe in toxic smoke. Teflon has a lot less toxic smoke. Still has toxic smoke. You get it hot enough, I imagine you'd probably be smelling the toxic smoke. But by that point, you probably would have had time to leave wherever is on fire. So is that clear? If there's a fire, make sure you get out. So here's just some different coaxial cable specifications. I'm not going to cover these too much. Main ones to know are just going to be RG6, which is of course going to use the F-type connector like I passed around. And pretty much all these others are going to use some sort of a BNC connector. You're not going to see them in 2021 very likely. I guess maybe some sort of old military installation might be still using some thin net variant, but for the most part, you're going to likely see RG6, which is what you're probably used to seeing and what I just passed around. So that's really all you need to know about that. Okay, let's shift gears a little bit now and talk about twisted pair. So I've got two examples here. The first is kind of like what we'll be doing in the lab, either Friday or Monday, depending on which lab day you have. But basically, as the name implies, there's twisted pairs. So you can see here, I untwisted the pairs on this one, and then on this other side here, I left them twisted, so you can kind of see that. So I'm just going to pass this around. And then I also have just a standard patch cable. Just pass them both. So for these, I mean, the patch cable, obviously try not to destroy it, but do whatever you want to the other one, to the one that's not having any ends on it. So, certainly have fun with that. But basically, like I said, it's got twisted pairs. And if you look closely, you'll see that each of those individual strands, or each individual cable, has its own insulation. So it's going to be colored. You got different colors on there. And basically, we'll talk about how you actually wire it up a little bit later. But just know those colors are very important for when it comes to wiring. Okay. So you also have two different types. You have stuff where it's unshielded twisted pair. So you can see there's no additional shielding. Shielding is going to help reduce the crosstalk or interference, specifically EMI. And it's also going to make it a little bit better for fire rating, although, again, just like with the coaxial, you want to make sure that if you're running it in between a fire barrier, that you're using an insulated, not just insulated, but that you're using plenum-rated cable. That's very important. If you don't do that and there's a fire and you're the installer, you could be sued. Anyone in here like to be sued? I didn't think I'd see any hands up for that question. So, certainly keep in mind, always make sure that if you're going between, and you guys know what a fire barrier is, right? So, don't quote me on building codes, but for residential structures, if things share an exterior wall, the minimum, at least in Georgia and Mississippi where I'm familiar with the codes, you have to have at least 4 pieces of half-inch drywall, or maybe it's 5/8 inch. Either way, at least 4 pieces of drywall. And that's supposed to stop the fire for at least 10 minutes from going between units. You also have, of course, more beefy sort of firewalls. And with those, the whole premise is that if the fire goes out the ceiling, it's not going to jump over to another ceiling. So you've probably seen those extend beyond the roof line a couple feet. And basically, if you're going through those, it's okay to go through those with the proper cable, with the proper sealant, and all that. So another advantage of these is that, generally speaking, twisted pair cable is pretty inexpensive, but it's not necessarily more expensive in bulk than, say, fiber or coaxial. The main benefit of twisted pair is to buy the tools to terminate it or to splice it or anything like that. Very inexpensive. In the lab, we managed to buy kits for, I think it was around $15 a piece. And that includes 100 ends. It includes a crimp tool. It includes a strip tool to strip the insulation off. So, like right here, just basically open it up and then spin it around, and it basically strips the insulation off. So, very beneficial from that perspective. But, like I said, there are some downsides. Since this is just a junk cable, I'll just go ahead and show you. If you bend it like this and you put a kink in it, you're liable to damage the inside strands. And if the strands are damaged, obviously they can't pass a signal. So it's not good to do this. Don't do this on any real cable, especially not one in production. But that one's just a piece of junk we can just play with however we see fit. So another downside is, and this is particularly true if you're doing a large building installation, if you're pulling the cables, they have a very low, I think it's called tensile strength, where basically you have 25 pounds of pressure you can pull, whereas with fiber, you have about 200 pounds of pressure. Now, fiber is a lot more fragile in other ways. We'll talk about that. But in general, 25 pounds of, pulling force, if you're trying to get it around a curve or you're trying to, I don't know, maybe it's stuck on something, 25 pounds is not a very large amount, is it? So it's easy to work with within reason, but it's not necessarily the easiest thing ever. Like I say, if you want to get the shielded twisted pair, it's a lot better to run near things that are going to cause EMI, like fluorescent lights, for example. In some cases, even, anything in the ceiling may. Not just fluorescent lights, those are probably the biggest offenders, at least in terms of stereotypes of large offenders, but there are certainly many other things in a ceiling that may cause problems. Sorry, guys. Probably should have silenced that before class. That's my bad. So anyway, go through these categories of the TP cable, the twisted pair cable, briefly. Category 1 is going to be for plain old telephone service. Didn't bring any examples of it. You've probably seen a telephone cable. Only has 2 pairs. Uses an RJ11 connector. Then we have category 2. It's going to go up to 4 megabits per second. Not the fastest cable in the world. Only goes up to 10 megahertz as well. So when you think about it, there's going to be a lot fewer twists per the same distance in these lower categories with a smaller megahertz range than the larger categories. Cat 3 is going to be up to 10 megabits per second. Cat 4 is going to be for token ring connections, up to 16 megabits per second. Pretty much anything from 2 to 4 you're not going to see. You may run into some Cat 3 on occasion, but for the most part, you're not likely to see anything but Cat 5 and up. So when we get to Cat 5, we get to more modern networking. Still talking like the 80s, but still. 100 megahertz, 100 megabits per second. That will be usable today. Not necessarily ideal, but certainly usable. Cat 5e is where it starts to get more familiar. So Cat 5e, the difference between it and Cat 5 is, for one, there's going to be more twist in 5e, and for 2, there's going to be a much larger speed. So we can go 1 gigabit per second. And the book has a funny comment in there talking about twisted pair cable and its benefits. They say it enables speeds that weren't possible a decade ago. Well, that's simply not true. There's no speed a decade ago that wasn't possible that is today because of twisted pair cable. I think that's pretty fair to say. In fact, I know that's fair to say. So don't pay too much attention when they talk about stuff a decade ago. I feel like the book was written 30 years ago. And anyway, not going to complain too much about that. Cat 6 is kind of unique where we start to get into sort of more fast sort of specifications. 10 gigabits per second at 37 meters. So if your cable is 37 meters or fewer, it is technically rated for 10 gigabits per second. Now, does that mean that if you make a cable exactly 37 meters, that it will always be able to sustain a 10 gigabit per second connection? Of course not. We're talking about physical things that are passed via, basically electric pulses. I mean, it's not going to be exact, 37 meters. There's certainly cases where you could use the proper cable, and you have to be very careful to meet whatever specifications whenever you're terminating the cable. Of course, anything beyond that, you can take it up to 100 meters, and it'll basically run a gigabit per second. Could run a little bit faster than that, but it doesn't have to. So in general, we're talking about networking. We're talking about the theoretical speed versus the actual speed. So just want to make sure that's clear. 5A just basically doubles the megahertz operating range right there, and it basically drops the length requirement as well. Well, let me rephrase that. Pretty much no copper cable can go more than 100 meters without having some additional power applied to it. That power could come from a switch. That's where it usually comes from. But you could also just have some other type of power injected into it. Not necessarily PoE, don't get those confused. But just any sort of powered interface card can allow it to go, basically extend the range. Eventually, you'll just have too much dB loss. It's not really sustainable. But in general, that's kind of what we're talking about there. 7 is going to be more for the core environment. It's not going to be so much for end users, especially not right now. But in general, you can go 10 gigabits per second. 7A. Again, all these 7A and 8. And I think they even have up to Cat 9 now. It's all going to be for core stuff. It's not going to be for some home installation or, even worse, some random desktop, having to have a 40 gigabit. We're not to that level yet. Will we be to that level in the next 10 years? I'd say it's likely. But right now, you're not going to see these in anything but a sort of enterprise core environment. So 40 gigabits per second at 50 meters, that's pretty fast. And then lastly, 8 is, of course, 40 gigabits per second at up to 100 meters. So I'm not going to ask you too much about the cats. Make sure you know Cat 5, 5e, and 6. I think those are probably by far the most important. Definitely the ones you're likely to see. I will say this, as you increase in the categories, you will definitely see more twist per whatever metric you want to apply to it. If you want to say twist per meter, twist per inch, doesn't matter. You're going to see more twist in the same amount of distance. So any questions about these so far? All right. So I'll talk a little bit about registered jacks. Going to be used for twisted pair. Probably should have brought one in, but basically just know that it allows each of the individual strands to have a pin associated with it. So if you look closely here, you can see there's 8 pins, and that's basically what allows the signal to pass through. Current Ethernet standards, for the most part, only use 4 of those 8. PoE uses an additional 2, of course. But in general, we have RJ11, which is going to be 4 pins in total. It's going to be used for phones. We have RJ45, which of course is going to be used for Ethernet jacks. And the wired standard for most Ethernet patch cables is going to be the T568B standard, although there's also, of course, the A standard, less commonly used. I would suggest that if you're going out into be a network engineer, that you know them both, because they are both still used. But in general, as long as both the ends are the same, the cable will work. So just kind of keep that in mind. Okay, now we're going to talk about fiber optic cables a little bit. And I believe that the fiber optic cable is actually broken, because when I tried to pass my laser pointer through it, it did not actually work. So we're going to try it though. So of course, with fiber optic cable, unlike all the other cables we've talked about, coaxial and twisted pair, we're using a digital signal that is literally light. So if this were to be connected to something that could power it, or quote power, because it's not really power, you would be able to look on the other end and you would see light emitting from it, typically red light. So I'm just going to turn off the lights here and see if I can get it to come out. Probably won't be able to, but we'll try it. So make sure I don't accidentally blind anyone. Make sure to point everything toward the... Actually, would someone mind holding this end for me? Appreciate it. If you'll just hold it against the whiteboard so we can see it. All right, let's see if we can get the light. If you'll hold it more like this so that the... And be careful not to touch the ends. Just like that, so that way we can see the light coming out of it. But make sure you angle it toward like that. All right, let's see if we can get the light to come out. Well, like I say, it's okay. So unfortunately, I think this cable has a break in it. Was very nice of the networking team to let me borrow some fiber patch cables. I certainly don't have them laying around. I'm going to pass these around. It's okay to look at them, but I would ask that you not touch the tips of them, because if you do, you might get oils on them, and that could certainly degrade their performance. It's possible to clean them off, but I'd just rather people not, touch the ends. So as you can see, these, of course, are using the angled pair connections, which we'll talk about in a couple slides. These do not appear to be using angled paired. But basically, we have different sorts of connectors on them, which we'll talk about in a couple slides here. But basically, these orange ones here, who can tell me what these are? So these are going to be called the straight tips, STs. This cable right here, the yellow one that I have in my hand, is actually pretty cool in that it has multiple types of connectors on it. So these right here, the smaller ones that are sort of together, these are the LCs, and these right here are the square connectors, which everyone refers to as SCs. So I'll go ahead and pass these around. Like I say, please don't touch the tips, but feel free to touch in the other part. Also, obviously, please don't bend them like I did the copper patch cable. So let's go ahead and pass those around. All right, and because it's not using any sort of a analog signal, or it's not using any sort of electricity to conduct a signal at all, it's not subject to EMI or RFI. So of course, we're talking about electromagnetic interference or radio frequency interference. So that's a very beneficial thing, because if we're running them through a ceiling or running them next to a lot of other cables, you don't have to worry at all about any sort of interference. And if we were to pop one of those open, which clearly we're not, but if we were to, we would see probably going to be a plastic for a patch cable, but there's going to be some sort of a very thin conductor. Well, it's not even a conductor. It's going to allow light to pass through. It's going to be very thin, and it's going to be made of either glass or plastic. And almost always going to have some sort of a stringy-looking Kevlar around it. It's going to be something to kind of help prevent it from breaking or cracking or fracturing or anything like that. And then, of course, you can see on the outside of it, you can see the sheathing there. Those are almost always going to be PVC for patch cables. And for anything that you're running anywhere, it's almost always going to be some sort of a plenum sheathing. Sometimes it could be Teflon. It could be a lot of other materials as well. One thing to make note of with fiber, you can do really long runs without powering the signal additional times. Having said that, most of the fiber that you see, and I mean physically see, is almost always only rated for 100 meters. So it's just like coaxial and really any of the types of cable, in that most of it still has to be powered every X amount of distance, typically 100 meters. But unlike some of the other types of twisted pair, you can go for potential, I think it's 30 or 40 miles with certain types of cable. It's very expensive to do that. And with fiber, unlike with copper, where I was talking about, you could buy the termination kits for like $15 on Amazon right now, probably even cheaper on eBay. Can't do that with fiber. So the cable itself is a very similar price in bulk to twisted pair. Where it gets more expensive is the ends to actually terminate it with, all that equipment, to splice it, to do anything with it. It's very costly. So Friday or Monday, depending on when you get a chance, I recommend you guys ask the networking team to talk to you about terminating fiber cable. So Fort Lewis actually has the equipment to do so, but even then, even to use it for a marginal cable termination is potentially hundreds of dollars. So even with the equipment, it's still quite costly. But that said, if you bring a contractor in, it's a lot less than hundreds of dollars, especially if you're doing multiple terminations. That said, it's probably still $100 minimum of termination. So, any questions about fiber optic cable? Yeah. Yeah, great question. The main thing is going to be it's a fixed cost. So an ISP, if you think back to Porter's 5 forces, what's on the top? It's threat of new entrants. And one of the main drivers of threat of new entrants is the upfront cost to establish a business. So in general, if we think about a business, what is the actual capital needed to have the business? It's property, plant, equipment. So in other words, if I pull up a balance sheet and we have property, plant, equipment on there, that is every piece of equipment that the business owns. That is every piece of property they own. It's every building. And basically what that's saying is, if you have any company, you look at that number, that is basically what you would need, well, relatively. That is what they needed, at least, to get to where they are. Not talking about employees, not talking about intellectual capital, just in terms of physical capital, property, plant, equipment. So running fiber optic cable is quite costly. So if you have a neighborhood, and let's say it's a pretty rural neighborhood, each home has, I don't know, let's say 125 feet of front yard. So you have to run, at minimum, 125 feet just to go through the neighborhood for each individual customer. Now, fiber, we think it's going to cost at least, and we're talking about a municipal installation, it's going to cost at least $1,000 a mile to run it. So if you're spending $1,000 to run down one street, and that's the minimum cost, it's very likely to be above $10,000 per mile. Because there's all sorts of permits, you have to call before you dig, which is free, but actually looking at the data, sort of determining where exactly you can dig, let's face it, if you're digging, is all soil the same? No, it's not. So you may have to burrow 10 feet underground. That's costly. So everything in here is going to be very costly. It's going to have a lot of fixed costs. So one solution to this is a wireless ISP, a WISP. Why is a WISP more cost effective? Well, think about it. You have to have a lot fewer runs of fiber. So not only would you have to have it run all the way down the road, you have to run it to the house, and that's also costly. Whereas a WISP, all you have to really do is just find some high ground set up a basic tower, and you can get the equipment for just a couple $1,000s. Not very costly at all. Now, having said that, you have to have some pretty beefy service to that point, but that can still only be a couple $1,000. Just run it off some existing dark fiber. So there's a lot of different ways to kind of think about it, but in general, we're talking about why there are not more fiber optic ISPs. It's all about fixed cost. It's very costly, and unless you're in a very dense area, you're unlikely to recoup those costs for a reasonable amount of time. So in business, a good rule of thumb for if a project is worth it or not, it's not the only rule of thumb, clearly. But one thing to think about is, are you going to make your money back within 2 years or less? If the answer is yes, then maybe it's a good thing to do. If the answer is no, it's probably something to maybe consider, but not necessarily jump on immediately. There's going to be a lot of other factors to keep in mind. For example, let's say you're in an industry that has a large number of regulations associated with it. You may be required to do something that doesn't make financial sense. Do you still have to do it? Well, it depends on what the penalties are for not doing it. Now, I'm being clear. I'm not saying to ignore regulations, but if the penalty for not following regulation is a $50 fine and you're saving $1 million a year by not doing it, does it not make sense to not do it? I mean, clearly it does make sense to not do it in that circumstance. So it's kind of a roundabout way to answer the question, but just think about the high fixed cost of running fiber. It's going to be very costly. Like I say, the minimum you're spending to run a fiber cable is $1,000 a mile. You're going to be spending way more than that in practice. Any other questions? All right, so talk a little bit about different types of fiber. You have single mode fiber, which is going to be a lot faster, and basically has a single strand, allows us to go very long distances. The book quotes about 50 times multi-mode fiber. I don't know that I'd agree with that in practice, but it'll certainly be substantially more than multi-mode fiber. Having said that, multi-mode fiber has a lot of other advantages. It's almost always what you see run within a building. It's almost always what you see in a patch cable, because not only is it cheaper, it's also a lot less fragile. So if you're running the cable and you accidentally cut a bend too sharply, you're a lot less likely to break something that has multiple strands than it has a single strand. A lot of physics behind that. It's not a physics class. Just understand multiple strands are going to help provide it some support to not sort of fracture, and just be a lot better overall for those purposes. But certainly if you're going a long distance and speed is a big concern, we're talking 10 gigabit per second plus, because multi-mode fiber can easily hit 10 gigabits per second in most cases. But we're talking about something that's going between buildings, and you have the land, and you can run it above ground. Definitely go single mode. You don't have to, but it's certainly going to be a lot better for most of those sort of cases. So everyone kind of understand the difference between single and multi-mode fiber? All right. Now let's talk about different sort of cuts of the cable. So if you look in the book, they don't really do a great job showing a picture of the differences between angled physical contact, which you see right here, and ultraphysical contact, which is like a dome. They don't do a great job of showing that. But just look at the actual tip of the fiber, and you see it's at an angle. It's going to be angled physical contact. If it's sort of like a dome, that's going to be ultraphysical contact. So basically, in general, there's going to be some cases where you'd want to use one over the other. Certainly for durability, ultraphysical contact is going to be a lot better, because what can happen over time as you plug and unplug, or as more commonly referred to in networking, as you mate cables, you're going to certainly see that this tip is going to dull. And what happens when the tip dulls is it's not going to reflect the light nearly as well. So in general, you know, it all depends on what you need. If you need something to be very durable and support lots of connections or matings, then ultraphysical contact is probably going to be better. If you're just concerned about speed, reducing the dB loss, then angled physical contact is probably going to be superior for that. So is that clear to everyone? Like I said, if we look at the cable, so if you look really closely on this, you can actually tell it is angled physical because you can see it has a very slight angle associated with it. So it's probably going to be better for those purposes, but there are cases where you use one over the other. Okay, so we talked about connectors a little bit. So straight tip, it's going to have the transmit and receive separated, and it's basically just going to be something you plug straight in. Most of the time it's going to use a BNC connector. So basically you plug it in and twist, kind of lock it into place. It's basically a straight tip connector. The square or SC connector, I don't know that it's square. I think it's more of a rectangular shape, but it's one that looks like a square almost. Basically, transmit and receive are also separated, and it's going to be something you're going to see a lot of in older installations. These two are definitely older technologies, whereas MTRJ, that's a newer technology, but it's a lot less common for new installations. What you're a lot more likely to see for new installations is LC. It's like this right here, where they're separated strands, but yet it's a single connector. So you basically plug it in and do that. So those are the basic types of connectors. In general, they're going to be compatible. Like you can see, we have different connectors on the same cable. So we're going to talk a little bit about those sort of exchanges. But if you're going across the same medium, you don't have to change the end. You don't have to change the whole cable to change the end. You can basically do it on the same. So if I were having a copper cable, and let's say it were coaxial, one end could be BNC, the other could be an F connector, F-type connector. It doesn't really matter because it's the same type of signal. It's only whenever you change the type of signal that you need to convert it to something. So a transceiver is going to be something that's going to allow us to basically use fiber on a switch or fiber on a router. Now, what's that one reason why we don't see just like a straight tip port, for example, on a router or a switch? Any ideas? Okay, so how many different types of connectors are there? First of all, this is not all the connectors. There's a lot more than this. These are the common ones, but these are not at all a full exhaustive list. So many different types of fiber. So what we actually use is something that's going to allow us to support all of them. And it's called SFPs. I don't have any with me, but basically they look like this. So you have an end, and then you have another end, and this goes into the router or switch, and then this end has the ports for your fiber connection. So SFP is definitely going to be the more common one that you'll see on, nowadays I would say mid-grade or below equipment, but we also see quad SFP, which is going to allow us to hit up to a theoretical speed, 100 gigabits per second. So basically has 4 channels, each 28 gigabits per second, and that's pretty fast. So if you see a quad SFP, you could be hitting 100 gigabits per second on that. But like I said, a lot more common is you'll see an SFP. So basically all it does is just allow you to use fiber in a switch or router, because most of the time that's going to be built around copper connections. And why don't we have those for copper? Specifically twisted pair. Well, we don't need them, because with the copper twisted pair, how many types of connection are we likely to see? We're likely to see RJ11, and that's basically it. So there's no real need for them on that. Just whenever you have a bunch of different types of connections, that's where this becomes a bigger factor. Any questions? All right, so now converters. I don't see a whole big reason to go into a lot of stuff about converters. They exist. Just know that if you need to go from, say, fiber to copper twisted pair, you can. Certainly find and research the appropriate converter. And all it does is convert something from one type of signal to another. Not to be confused with a modem. Why is this not a modem? So what is a modem? Exactly, it's a modulator, demodulator. That's a lot different than something that's just converting one signal from one type to another type. So just want to keep that in mind. Just know that they exist. That's all you need to know there. Talk briefly about serial cables. Don't need to go a whole lot into this. But basically, back in the day, if you wanted to convert or connect rather to a switch, they had a console port on them, and then the console cable looked a lot like an RJ45 end. It was not an RJ45 end, but it looked like it. And on the other end, you would have what's known as a DB9 connector. So RS-232 is that cable name, but the port that it connects to is called the DB9. And that's basically how you would connect to a switch or a router to do any sort of maintenance on it, any sort of programming, anything like that you needed. But basically, with a serial cable, unlike a parallel cable where all the bits are read together, serial, of course, means that they're read one at a time, separately from each other, which, while it may sound slower, is of course much faster, because we're not having to read all of something at a time. Think about a parallel port. What were those commonly used for back in the day? The big sort of pink or purple connector, maybe maroon, whatever color you want to see there. What were those used for? Printers. Do printers need to go very fast, especially back in the day when they're printing basically plain text? No, they don't. So serial cables allow us to have a lot more data go across at a time, even though they're going to be read one at a time. Of course, we're not going to use that for most stuff today, because most of the time now, we're going to use something like USB for plug-and-play compatibility. What does plug-and-play mean? Exactly. So you think about a connector like PS2 connector, for example, not PlayStation 2, PS2s and IBM PS2. Old style keyboard and mouse connectors. You guys know what I'm talking about? What happens if you unplug those while the computer is on? Well, the keyboard is obviously disconnected. What if you plug it back in while the computer's on? So not with PS2. With USB, you would be, because it's plug and play. But with PS2 connection, it's not plug and play. You have to reboot to be able to use it. That's why on a lot of computers, even today, but especially back 15, 20 years ago when PS2 was the standard, that's why you almost always saw that the computers had a BIOS warning that if there was no keyboard attached, it wouldn't let it boot up all the way, or at least give you a warning, tell you to press F1. Well, the joke's on you. You don't have a keyboard attached by that point. You're not pressing F1. So it makes you reboot anyway. So that's what we're talking about with plug and play. It's a very beneficial thing about USB is that it allows you to plug and unplug a device without rebooting. Wouldn't it be a real pain if you had to reboot every time with a USB cable? Would that excite anyone? No computer reboot fanatics in here? Okay. Another limitation of USB, 127 devices max per controller. Of course, you can have multiple controllers and certainly get above that. Most consumer devices have a single USB controller. There are some exceptions to that, though. Think back to like around 2009, 2010, 2011. What was the difference between USB 2 and USB 3 back then? Well, still the difference today. There's a big speed difference, but one of the sort of key things is that neither AMD nor Intel's processors had a built-in USB 3.0 controller. So it's not uncommon to see laptops that have some ports that are blue for USB 3 and some that are black for standard USB 2 from that era. And most of the time, there's a separate USB 3 controller somewhere on the motherboard of those devices. So you could definitely get above 127 devices by having multiple controllers. The single controller can handle 127 devices. Does that make sense? All right. So now how do you pick out a cable? If I were to go up to someone, and let's just say I was to pick a random person in here, say I were to go up to Ben, and I would ask him, Ben, how are you going to pick your cable? How would you do it? What about cost? Cost is almost always going to be the most important thing to consider. second only to strategy. But I would argue that cost is typically going to be a part of strategy. We think back to some of Porter's strategies. We have cost leadership. Literally has cost in the name, does it not? Then we have differentiation. Differentiation, we're a lot less focused on cost, but for a cost leadership firm, we always think about cost. And that's the cost of everything. That's not the cost of an individual cable. It's the cost of the installation. So it may very well be cheaper to buy fiber multi-mode, maybe 1,000 feet of it, than it would be to buy just standard, twisted pair Cat 6. That's very well possible. Not saying it is, probably won't be, but it could be. But that's not the whole cost. You also have to think about how much is it going to cost to terminate each of the ends. How much is it going to cost for us to make ports? How much is it going to cost to do splices? All those are things we have to consider. So that's going to be very important. Frequency. So frequency is going to be important as well. Let's say that we have some data that needs to be done very quickly. Well, obviously, we're not going to be using Cat 5 for that, so just make sure to keep that sort of stuff in mind. Noise immunity. Let's say we're having to do an installation that has, let's just say 100 different strands of cable going down right next to fluorescent lights and inside of the plenum space. What type of cable do you think we're going to use for that? And why? Yeah. You could. That would certainly be one option. But also make sure to add shielded twisted pair plenum rated as well. That would certainly be an option. Let's say you have to go 150 meters with that many cables. Then what would you pick? So there's going to be a lot of different sort of interference. Exactly. Why would you pick fiber? Yeah, can interfere with light, especially when it's inside of a encased sort of container. So duplex, honestly, I mean, that's not something I would personally consider. I don't really know why the book says to consider it. With fiber, you have separate strands for send and receive. Having said that, it's not really a downside. I mean, it's just something to keep in mind. And the reason I say it's not a downside is because, well, how is it a downside to have different strands? I mean, technically speaking, copper, you think it's sending the same signal across this? No, it's got 8 different pins to use. So I wouldn't worry too much about it. You certainly could if you wanted. Basically, look at cost, look at noise immunity, look at transmission speed, look at distance. Anything else we forgot? So that basically covers it. Definitely think about fire rating if you're having to cross any sort of fire barrier. And that's something you check with whatever site you're on. Look at the building plans. It'll have it marked on there. Firewall. If you're having to go across that, you make sure to use plenum-rated cable. Of course, also make sure to seal any openings that you create. What happens if you don't seal it and it's a firewall? So smoke can pour through it quite easily. That could be a problem. And then also fire could get through it pretty easily. That's another problem. It's important to remember that fire, you don't have to touch a flame to ignite something. I think some people, or not some people, but it can be easy to forget that. To ignite something, you have to light a flame to it. You don't have to. Heat can ignite it as well. So if you insulate that opening, it's a lot less likely to have the heat pour through it. Make sure you use proper insulation. I don't know off the top of my head what that would be. If you're ever doing a job like that, make sure you research it. So some stuff to keep in mind. Kind of going back to twisted pair a little bit, different wiring standards with it. Basically we have T568A, T568B. We will see examples of those in the lab Friday or Monday. Just know that most stuff's going to be using T568B, but as long as both ends are the same, either will work. If you have one end that is T568A, and then another that is going to be B, what's that cable called? It's a crossover cable. Back in the day, you used to have to use those to connect a router to a switch, for example. And what they allowed was to have the communication sort of be negotiated between those two. Nowadays, it's pretty much irrelevant because pretty much everything from the past 10 years on in the enterprise space is going to use auto negotiation, so that you don't really have to use a crossover cable. Maybe even more than 10 years, but at least the past 10 years, it's been almost irrelevant. I mean, you can still use it, but it's also like, why not just use regular patch cable, make life a lot easier, have one type of cable, and let auto negotiation handle everything. So that's going to be common on pretty much any type of enterprise environment you'd see. A little bit about wiring distributions. So obviously, you have some signal coming in. You have to get it out to whatever building or campus you're using. So within a campus, we're going to have a main distribution frame, some place in which the cable signal comes in, and we basically give it to the whole building. Within a building, you're going to use an intermediate distribution frame. Again, it's going to be building specific. Each building would have one. Then, of course, we have the demarc, or demarcation, and just a fancy way of saying it's where the ISP's responsibility stops. So it's going to be the point in which they're no longer responsible for what happens on your network. So if they can test their signal and it's good up to that point, whatever the problem is on you or whoever the network engineers may be. And then lastly, patch panels are going to be used to sort of make life a lot easier when you have lots of different strands of, in particular, twisted pair cable coming in. You basically put them in a patch panel, and then one end of the patch panel is going to be almost raw copper in a way, and then the other end is going to be nice little ports you plug in. You take that signal from the port, put it into your switch, and then that's how you would do it. Very unlikely to see an enterprise environment run without a patch panel, where they basically just have strands of copper hanging down from the ceiling with terminated ends on them. A lot more likely to use a patch panel. So just kind of wrap things up. We talked about physical media, talked a little bit about different cable properties, some wiring standards. And we wrapped up today by talking about installing wiring distributions. Any questions? All right, I will see some of you Friday. Some of you will be with the networking team. I shouldn't have to say this, but please be respectful to them. Ask them any questions you like, of course. They're going to be a great resource for you all. They know a lot. So anyways, have a good weekend if I don't see you Monday. Yeah. Yeah, that's right. Yeah, so you'll meet in here Monday if you're Group A.